आज हामी नेपाल गणित समाज र सेन्टर डिपार्टमेन्ट म्याथमेटिक्स त्रिभुवन युनिभर्सिटीको संयुक्त आयोजनामा यो विगत धेरै समयदेखि हामीले टक सिरिज सञ्चालन गरिरहेका थियौँ। त्यसको आज 13औं श्रृङ्खलामा छौँ र आजको रिसर्च पर्सन हुनुहुन्छ विष्णु लामिछाने सर। उहाँले हामीलाई पहिलेदेखि धेरै यो सोसाइटी डिपार्टमेन्टको सहयोग गरिराख्नु भएको छ। आजको यस प्रोग्रामको अध्यक्षता ग्रहण गरिदिनुहुनको लागि नेपाल गणित समाजका सभापति प्रोफेसर डाक्टर नारायण प्रसाद पहाडी सर र सेन्ट्रल डिपार्टमेन्ट म्याथमेटिक्सका विभागीय प्रमुख प्रोफेसर डाक्टर चेतराज भट्ट सरलाई म संयुक्त रूपमा हार्दिक अनुरोध गर्छु। भट्ट सर एन्ड पहाडी सर। आजको रिसोर्स पर्सन हुनुहुन्छ डाक्टर विष्णु लामिछाने सर। उहाँ युनिभर्सिटी अफ न्युक्यासल अस्ट्रेलियाको एसोसिएट प्रोफेसर पनि हुनुहुन्छ। उहाँको धेरै रिसर्च पब्लिकेसन पनि छ, धेरै स्टुडेन्टलाई पिएचडी पनि गरिराख्नु भएको छ। रिसर्चमा एक्टिभली एकदमै नेपालबाट बाहिर बसेर एक्टिभली रिसर्च गर्ने मध्येको प्रमुख व्यक्तित्व पनि हुनुहुन्छ र आजको उहाँको टाइटल छ रिसर्च इन म्याथमेटिक्स, यसको टुल्स, रिसर्च प्रपोजल र मेथोलोजी सम्बन्धी जनरल खालको उहाँले आज सेसन लिँदै हुनुहुन्छ। टेन्टेटिभ हामीले 2 आवर्सको हामीले यो सेसन प्लान गरेका हौँ। अब विष्णु सरले कति हुन्छ र पार्टिसिपेन्टको इन्ट्रेस्ट अनुसार यसलाई घटाउने बढाउने विष्णु सरलाई हामीले उहाँलाई नै छोड्छौँ। र आजको यस प्रोग्राममा आफ्नो यो सेसनलाई अगाडि बढाइदिनु हुनको लागि म डाक्टर विष्णु लामिछाने सरलाई म हार्दिक अनुरोध गर्दछु।
Thank you, Jeevanji. Thank you, Chetra sir. Thank you, Narayan sir. Thank you for this invitation. It is my pleasure to talk about research in mathematics. I think research in mathematics is extremely broad, and everybody talks about from their own perspective. Like if I talk here, that would be from my own perspective. मेरो area, research area र मेरो पर्सपेक्टिभबाट मात्रै हुनेछ. That is why it will not be taken as a kind of broad general advice. It's like you can think that this is the experience. This is my experience in teaching, and this session should be really informal. Kind of informal in the sense that you guys can ask questions whenever you want. Just raise your hand or send me a chat message, and we can make it like an informal session. Sometimes I'll also go to, after I talking a little bit, I'll also go to discuss from Google Scholar. I use Google Scholar a lot, and there are a lot of tools that we can use for mathematical research from Google Scholar. And now starting with a very general setting here, mathematics is a very vast subject now, and it's not really easy to understand or get hand on every branch of mathematics. If we do research, or if we understand, that will be one small part of mathematics. There are many areas. Broadly, there are 3 main areas: pure mathematics, applied mathematics, and computational mathematics. I mean, there is also mathematical physics, which we can think of like applied mathematics. But in many countries, applied and computational mathematics can be in a single title. Like if you do research in computational, that can be also applied mathematics. And it is because it is so vast that a researcher in one field often doesn't understand the research in another field. Like if I have to study in research in like differential geometry, number theory, it would be not easy for me to understand those ideas. Even complex analysis, the research has gone really, really far in those areas, in all those areas, so that it's very difficult from one expert or one researcher in one field to understand research in another field. Even in the same field, like if 2 people are working on computational mathematics, like I work on the finite element method, I may understand most of the papers in finite element method, but if there is another area like new emerging area of virtual element methods, there are other areas like in computational mathematics, like finite difference method, and also mimetic finite difference method. There are many finite volume methods. Even some of the papers may not be easy to understand. And let me go to discuss briefly what is research, why we do research, and what are the objectives, and so on. research in mathematics, and research in any area is a systematic study. A systematic study of anything is research. It can be something new. It may not be something new. Like, okay, if I want to understand, what kind of people live in Bhutan, then it can be a research. That, okay, I go to a library, I go to Google, or I go to any online portal, and I want to understand what kind of people live in Bhutan, like, and then what kind of food they eat. That can be a kind of research as well. But research in academic platform or academic setting is something that we want to create new knowledge. In the context of mathematics research in academia, it is to create new knowledge. We want to create new knowledge. And here there are some examples here, and one can think of these examples as broad as possible, but may not be actually broad. The research can be theorem proving and problem solving. Mainly in mathematics, most of the research in classical time was focused on theorem proving and problem solving. Like, we have some problem, and we want to solve this problem, and we have a theorem and we want to prove that theorem, proving some famous open standing questions like Riemann hypothesis, P is not equal to NP, the existence and uniqueness of the solution of the Navier-Stokes equation. These are really famous problems. These are also in the list of Clay Mathematics Institute Millennium Problems. They are Millennium Problems, and I think when the solution of one problem is can get big prize as well. Here in this category, only a few mathematicians actually work, because these problems are so difficult to solve or prove, that unless you are in that kind of branch, in that kind of research area for a long time, it's not possible. And the second area is the area that we normally do all the time. I do, and I think most of the people who do research in mathematics, they do theory building and problem solving. That means we have some problem. We want to solve that problem by using some numerical technique. We want to solve that problem by using some theoretical approach. Then from that one, we will get some small theorems. We get corollaries and all these things. Then that also lead to new knowledge. While working on a certain problem, we can get some interesting mathematical structures which can lead to new theorems. Like, you can make some conjecture, and then you can work on that conjecture, and we can prove or we can disprove these kind of things. In the realm of problem solving, there are interesting problems of applying mathematical ideas to some real life problem. And this is the area which is extremely, let me underline here, this is extremely used in applied mathematics. We have some real life problem. We do mathematical modeling to that real life problem. We get mathematical model, and from that mathematical model, we go to computational approach. And if we can get analytic solution, that is good. If we don't get analytic solution, then we go to numerical calculation, and from the numerical calculation, we derive solutions, and we also validate that these are the solutions which are physically relevant. And if we do this one, these kind of research works will be publishable as well in some journals. And the other thing also, which is now intersecting with computer science, and also probably in physics, algorithm development and computer simulation, also in engineering and computer science. In engineering, most of the papers are mainly developing some algorithm for certain problems. And if there are some problems where still not really good algorithms are there, and developing algorithm for certain such problems would be actually very good research, and would be publishable. And we develop the algorithm in that area, and also develop the computers, do some computer simulation, present the computer simulation results, and that will be a nice journal paper, journal article. The other thing that we can also do mathematical modeling. There are so many problems everywhere we can see in our real life that can be used that can be very interesting from the scientific point of view, not only from the scientific point of view, that can be also interesting from the practical point of view, for industrial point of view. And then that leads to some sort of mathematical modeling, and using that modeling, we solve that mathematical model and present the results. That will be also quite interesting research article. Here, I want to quickly highlight that, for example, one problem that we have had in the past was image processing in image processing from radiation therapy. This is one problem. I work with some physicists, and also they work on cancer therapy using the image processing. They want to do this modeling by using mathematics, and then when we do the modeling, we also compute the mathematical model, solution of the mathematical model by using computer, and then we visualize the solution, and they compare that solution with their actual physical output. And that also lead to that has led to a few papers, few articles. Now I want to briefly discuss research in mathematics. Why do we do research? I think everybody knows why we do research. It's a necessary part of an academic job. In especially in the Western countries, or even in India, in Nepal as well now, research is obligatory. Like if you don't do research well, then you are not performing on your job. You are not doing well on your job, and you may be made redundant, or you may be, even fired from the job. This is a necessary part of an academic job, like teaching. You go to class and you teach numerical analysis, or you teach mathematical analysis. And if you don't do the teaching, then of course there is a question that why should they hire you, or why should they hire me? If you are a postdoc or a PhD student, research is the sole purpose of this position. And of course, then the research, if you do research intensively, it can open a new career path. Like if I start working on something, some industrial problem, I may quit my university job, and I may join join an industry to work on their problem. Or if you are working on as a postdoc or PhD, if you do research in different areas, then it can lead to another position, another higher position for you. Here in the first slide, I talk about why we do research, because this is the necessary part of our job. But in the here, we do research just to be keenly alive and spirited in the subject area. If we don't really do research, even the teaching can be, boring task. If you do research in functional analysis, and you go to teach in a class, you teach functional analysis in a class, you can make some relevant, examples. And also from the research, you have some excitement to talk about the subject area. Like I do research in finite element, I do research in numerical analysis. And if I talk about numerical analysis, I have a lot of practical examples to talk in the class. It's really important that we do research. Even those, those of you probably do only teaching, but even in teaching, there is a research component, that you find a new way of explaining something, like, new way of proving like Pythagoras theorem, a new way of proving some Ptolemy's theorem. And we find some new way of, proving or deriving the Lebesgue integral or something like that. And it may not be exactly new way of deriving, but explanation also can be new. And if you are being creative, then the class becomes lively. It doesn't become boring. To make the class lively, we want to do research. And the research is not only writing papers, or publishing and going to a conference. But research is also when you go to a class and teach, and you have, it is like thinking in a new way. How we understand some subjects, and of course to discover new knowledge and expand about what we already know. And for many people, it can be just hobby, and you may have your own reason to do the research. And now I will go to a bit more say formal way for the research objective. The main objective is to create new knowledge. Here I just described objective. methods, research ethics, and then we have the research output. There are four really important component in research. The main is the objective here. The main objective is to create new knowledge. As I mentioned before, it's already described in the previous slides, like developing new theory, proving some famous theorems, of solving some long-standing problems. But recently, in the numerical analysis, they developed virtual element method. That was definitely a new theory. Before that, like finite element method was developed, and then virtual element method. Maybe then there is also another one coming, weak Galerkin method. This is also newcomer. I think it has probably been introduced in 2015, 2016 around. And we can develop new algorithms. We don't need to do any theory, but we have some problems, and we implement that problem on a computer, and we found that the solution process is extremely slow. Now we start thinking, oh, this is very slow. How can I improve the timing? How can I make my algorithm efficient? We analyze the algorithm. Probably sometimes you can, just update some component of the algorithm and get good result, or working on that algorithm for a long time, it can be that you will develop some completely new algorithm. And another thing is the mathematical models and simulation, which is, I think, the most popular in mathematical research, because this can be done by most of the people in mathematics with some basic mathematical knowledge. Developing model, and model should be developed in such a way that we understand that model pretty well, and then we apply computer to get solution of those mathematical models, and those solutions are then validated against the physical problem. I will talk about the methods. I'll talk more detail today, and probably going into the Google Scholar and so on. There are many methods, and everybody has their own method. They may have their own method. Like some people go to a library and read papers. Some people go to computer and experiment some algorithm in a computer. A lot of thinking, putting thoughts in a systematic structure. And my strategy was that from my PhD, read as many papers as you can. That was my strategy. When I started my PhD, I was given a problem. In the first probably 6 months, I was given something to do the implementation. When I finished the implementation, then I was asked to write that results. I finished that, and after finishing that, I found that I have not really understood the theory. And now what I need is that I have to read as many papers as I can, and that was in the area of mortar finite element method. Most of you probably don't know what is mortar finite element method, but I think you know what mortar is. Mortar is when you join two bricks together. When you have two bricks together building a house, here I think the chemical is called mortar here. They put this cement, concrete, whatever it is, this is called mortar here. And in the finite element area, we have also here one brick here, and we have also another brick. Like here, we can have one kind of finite element in this area, and we can have another kind of finite element in this area here, like in these two bricks. Now the question is how to connect those two types of finite element solutions, and that leads to mortar finite element, and that was also a new theory developed in around 1998, I think. And then we developed some Lagrange. They use Lagrange multiplier. I think everybody knows what Lagrange multiplier is to deal with this. We call here non-matching triangulation here on the interface. We use Lagrange multiplier, and then there is also big branch of research that what kind of Lagrange multiplier should be numerically efficient. That's one thing. Numerically efficient is one. The second one is approximation. optimal for the approximation. Of course, it should be also easy to implement, the third one. These three components, easy to implement, numerically efficient, and theoretically optimal. These three properties, then that led to some bi-orthogonal system. That was my part of the research that I did most of the time in my PhD, also my postdoc. And also still now I'm working on some of the problems using bi-orthogonal system. I'll briefly describe that. And the ethics. This is really important in the West, the ethics, honesty and expressing the true finding, and properly citing the source if used in the research, not copying from any other place. If we use results from any other research article, that has to be cited properly. And this is really important. The research ethics is really important. And here, if it is found that somebody has copied from somewhere, or there is some ethical problem, there is no reason that that person will be hired in the university. That person will be completely easily fired. But by the way, I have to mention one thing, that you may sometimes publish the wrong result. That's not really non-ethical, okay? We are all human beings. We make mistakes. And in mathematics, it happens sometimes that we don't really find that results are wrong. Publishing wrong results is not non-ethical. It can be, it is quite ethical. But deliberately making wrong results, listing wrong numerical, for example, experiments, is non-ethical. And if it is found, then that person may be easily fired from the university job. Now, when we write our research finding, then we want to publish. Research output can be journal article. You can also see the ranking using the impact factor. By the way, there are so many journals, flourishing due to the, I think, due to the internet and due to the open access facility, and they can charge some money for the publication. And some of the journals are probably okay, but there are so many journals that don't really publish good articles. They publish whatever they get, they publish, which is not really good. The conference paper can be refereed or non-refereed, and we can have book chapter, we can have research monograph or research book, we can have preprint or technical report. Technical report, I think, is often published in archive, which is hosted by a university in the USA. I also sometimes published in archive. It's really important that when we finalize our paper, we can publish in archive so that nobody can copy our research. And we can also have survey, a review article, and also some poster presentation is also very much encouraged for PhD students. Literature is really important in mathematical research. If we want to do some research in, like, for example, homotopy method, then I go to Google Scholar and type homotopy method. Or if I want to do research in weak Galerkin method, I go to Google Scholar and type weak Galerkin method, and I can see a lot of information from there. I'll discuss that in detail in a minute. I use Google Scholar in daily basis, and I also use resources from library. But nowadays, we don't need hard copy books. We don't need so many hard copy journal articles, because we get most of them electronically. And we have also mathematics books, and conferences and meetings can also be very good platform for invigorating our research enthusiasm. And then research presentation. This is also very critical if you want to, like, go to some teaching job in the Western countries. The presentation should be precise and concise. We organize our research finding in a good structure to show to other colleagues or academics who might be interested in knowing what we have done. And from the research presentation, we can invite collaboration. If someone sees your presentation is interesting, they will contact you, and then they will be interested in doing work with you. A lot of my collaboration actually started with the research presentation. Once it happened that it was in Melbourne. I went to Melbourne for Australian Mathematical Society meeting. I was hosting computational mathematics session, and that year they overlapped two conferences. The computational conferences was separately done in Brisbane, and that AustMS, Australian Mathematical Society meeting was done in Melbourne. Because of that overlap, there were very few people attending that conference in Melbourne. But I went to Brisbane, and from Brisbane I flew to Melbourne to host the session. And I got one guy, he was from France. He was here, I think, in Monash University as a contract position. Then he presented something in, I think, gradient research. And I was interested. We talked about that. From that meeting, we published around 3 journal papers, pretty good journal papers, jointly. Research presentation can be very important if you want to develop your collaboration, increase your citation, and increase the impact of your research. In mathematics, I use Beamer to prepare presentation. This is also prepared with the Beamer. PowerPoint slides are also used, but they are not often used. They are rarely used in mathematics presentation. Let's discuss research area. We have to find the research area. For example, what I want to do in my research. For example, in the undergraduate level, one has to decide whether one is interested in pure mathematics like partial differential equation, group theory, functional analysis, numerical analysis, or something like that. And then they have to talk to the relevant professors. And then from that one, they might get some problem. And from that problem, if you work on that problem for maybe one year, and so you yourself will see a lot of open problems. And then if you can't even solve that open problem, some aspect of that problem can be also studied. Important thing in research is that it's very important to connect the work with already existing literature. Like if we do develop some new theory, but if the new theory doesn't have any connection with the existing literature, nobody will publish. And there should be some sort of connection that connection should be made really clear. And the another thing is extensive literature search, mostly using Google Scholar, or I can also use my library to search. From that one, we know that whether the problem is discussed before, and we can link the current research with the existing literature. And we often need only the main idea of the paper, not the whole content. Sometimes you just read the abstract of the paper and see what they have done. And then from that one, you can just go ahead. Now, let me briefly go to open the floor for discussion. And I want to also show how I use Google Scholar on a daily basis. अब केही क्वेसन छ साथीहरु छ भने क्वेसन सोध्नु होला। अब मैले एकछिन चाहिँ गुगल स्कलरमा कसरी रिसर्च गर्ने, कसरी इन्फर्मेसनहरु लिने भन्ने बारेमा मेरो आफ्नो एक्सपिरियन्स देखाउँछु। हजुर कुमार जी भन्नुस्।
सर नमस्कार।
हजुर
सबै
नमस्कार।
सर म्यामहरुलाई नमस्कार। बडा इन्ट्रेस्टिङ चाहिँ भइरहेछ टक। मैले यो एउटा मेरो सानो जिज्ञासा समस्या भन्नु सरसँग अनुरोध गर्न खोजे। हामीले मेथोडोलोजीका कुराहरु, मेथडका कुरा डिस्कस गर्यौं हैन सर?
हजुर।
यो विशेषतः हामी एनालाइसिसतिर हैन, फंक्सनल एनालाइसिसतिर अथवा म्याथमेटिकल जे भनौं, त्यो न्यू रिजल्टहरु हामी एस्टाब्लिश गर्छौं नि सर।
हजुर।
अब त्यो खालको रिसर्च गर्दा चाहिँ त्यसलाई चाहिँ यो स्पेशली एजुकेसनतिरका साथीहरुले धेरै खोज्दा रहेछन्। यो यसको नेचर कुन हो भनेर, क्वालिटेटिभ नेचर हो कि क्वान्टिटेटिभ नेचर हो भनेर क्वेशन राख्छन् के।
हजुर।
अनि यो चाहिँ म क्लियर नभएको कुरा भएर हजुरलाई अनुरोध गरे। अनि स्टडी मेथडहरुमा पनि उनीहरूले यो कस्तो खालको मेथड हो यहाँ प्रयोग हुने अथवा डिजाइन भन्नु रिसर्च डिजाइन भन्दो रहेछ नि डिजाइन चाहिँ कस्तो डिजाइन हो त त्यो डिस्क्रिप्टिभ डिजाइन हो कि एक्सप्लोरेटिभ हो कि एक्सपेरिमेन्टल हो कि हिस्टोरिकल हो या एनी मोर अरू लाइब्रेरी यो स्टडी मेथड यो मेथड डिजाइनको कुरा र नेचर क्वालिटेटिभ क्वान्टिटेटिभ के हो भन्छन् यो जुन रिसर्चमा हामी चाहिँ न्यू रिजल्ट्सहरू चाहिँ इस्टाब्लिस गर्छौँ स्पेसल्ली एनालाइसिससँग रिलेटेड यति जिज्ञासा मेरो राखेँ
हस् हस् थ्याङ्क यू तपाईँको क्वेसन चाहिँ भास्ट रह्यो होइन अब मैले जति जानेको छु मेरो आफ्नो एक्सपिरियन्सबाट मैले बताउँछु अब क्वालिटी र क्वान्टिटीको कुरा चाहिँ गर्दाखेरि के हुन्छ भने जस्तो एउटा थियरम तपाईँले प्रुभ गर्नुभयो होइन जस्तो एउटा इक्जाम्पल लिउँ पाइथागोरस थियरमकै इक्जाम्पल लिउँ तपाईँले चाहिँ 10 लाइन्समा प्रुभ गर्नुभयो एउटा थियरम्स अनि अर्को साथीले चाहिँ 5 लाइन्समा प्रुभ गर्नुभयो 5 लाइन्समा होइन 10 लाइन्स 5 लाइन्स 10 लाइन्सको चाहिँ विद्यार्थीहरूलाई एकदमै सजिलो एक्सेसिबल भयो होइन 5 लाइन्सको चाहिँ एक्सेसिबल भएन अब क्वालिटेटिभ र क्वान्टिटेटिभ तपाईँ आफै विचार गर्नुहोस् त्यो दुईटा थियरम प्रुफमा 5 लाइन्सको थियरम प्रुफ चाहिँ रिसर्च गर्ने मान्छेको लागि जो मान्छेले त्यो रिजल्टलाई चाहिँ त्यो प्रुफलाई युज गर्न खोज्छ त्यसको लागि युज हुने भयो इट्स भेरी इजी टु मेमोराइज 10 लाइन्सको प्रुफ चाहिँ तपाईँको विद्यार्थीको लागि युज हुने भयो किनभने इट इज मोर एक्सेसिबल टु स्टुडेन्ट्स त क्वालिटीको कुरा चाहिँ त्यहाँबाट आउँछ यो पर्सनल क्वालिटी भनेको चाहिँ एउटा पर्सनल आस्पेक्ट पनि हो होइन हानमानक थियरम फर इक्जाम्पल सबै साथीहरू जसले मास्टर गर्नुभएको छ नेपालबाट हानमानक थियरम पढाइ हुन्छ होइन हानमानक थियरमको प्रुफ इट इज भेरी लङ what we saw in this functional analysis book, I think we use, I forgot the name of that guy, applied functional analysis, I think we use that book. अब कसैले त्यो प्रुफलाई चाहिँ सजिलोसँग छोटो बनाएर प्रुफ गर्न सक्यो भने क्वालिटेटिभली दिस क्यान बी क्वाइट गुड इम्प्रुभमेन्ट त्यसै भएर प्रुफको क्वालिटी चाहिँ के हुन्छ भने कुनै प्रुफ कन्साइज प्रिसाइजको साथै छोटो भयो भने र सजिलोसँग एक्सेसिबल हुने भयो भने त्यो प्रुफलाई राम्रो मानिन्छ तपाईँ अब यो एउटा इक्जाम्पल मैले फर्माट्स लास्ट थियरमको इक्जाम्पल दिन्छु होइन फर्माट्स लास्ट थियरम चाहिँ 1998 तिर हो कि 1999 तिर प्रुफ भयो अनि त्यो प्रुफ भयो बट इट वाज नट एक्सेसिबल टु एभ्री वान इट वाज भेरी डिफिकल्ट टु अन्डरस्ट्यान्ड एन्ड द सेम गाई went back and tried to make it easier, and then he found some mistakes in his proof, and he corrected his proof, and then he made that proof accessible later on. Qualitatively त्यसरी चाहिँ म्याथमेटिक्स चाहिँ इम्प्रुभ गर्न सकिन्छ एउटा हिलबर्टको भनाइ छ यो मलाई साह्रै नै घट लागेको भनाइ हो यो इम्पोसिबल जस्तो लाग्छ मलाई चाहिँ उसले भनेको छ कि कुनै पनि म्याथमेटिकल थ्योरी त्यति बेलासम्म कम्प्लिट हुँदैन जति बेलासम्म त्यो म्याथमेटिकल थ्योरी चाहिँ तपाईँले बाहिर हिँडिरहेको बेलामा एकजना भेट्नुहुन्छ र त्यसलाई एक्सप्लेन गर्न सक्नुहुन्न भने त्यो म्याथमेटिकल थ्योरी कम्प्लिट हुँदैन भनेर हिलबर्टले एक ठाउँ भनेको छ कि अब हिलबर्टको त्यो एप्रोच इम्पोसिबल होला तपाईँ बाहिर हिँडिरहनु भएको छ हिँडिरहेको मान्छेलाई हानमानक थियरम बुझाउन त गाह्रै होला होइन काठमाडौँमा हिँड्दा हिँड्दै कोही मान्छे भेट भयो त्यसलाई चाहिँ तर भन्न खोजेको कुरा चाहिँ के हो भने यु हेभ टु मेक म्याथमेटिकल थ्योरिज एज एक्सेसिबल एज पोसिबल त्यो क्वालिटेटिभ र क्वान्टिटेटिभको कुरा चाहिँ त्यो हो तपाईँले एउटा अर्को कुरा चाहिँ यो रिसर्च डिजाइनको र मेथोडोलोजीको कुरा गर्नुभयो होइन म्याथमेटिक्समा चाहिँ सामान्यतया रिसर्च डिजाइन भन्ने त्यस्तो हुँदैन तपाईँ स्ट्याटिस्टिक्समा जानुभयो भने रिसर्च डिजाइन हुन्छ डाटा कलेक्सन हुन्छ होइन एक्सपेरिमेन्टल डिजाइन हुन्छ तपाईँले एक्सपेरिमेन्ट गर्नुपर्ने हुन्छ म्याथमेटिक्समा तपाईँले चाहिँ एकदमै रिसर्च इन्डस्ट्रियल काम गर्नुभयो भने त्यहाँ एक्सपेरिमेन्टल डिजाइन होला त्यो पेपर चाहिँ मोस्टली इट विल गो टु सम इन्जिनियरिङ जर्नल्स रेदर देन म्याथमेटिक्स जर्नल इन मोस्ट अफ द म्याथमेटिक्स जर्नल्स the papers they don't have this kind of experimental design and research methodology type of thing. If you have something like that, they can be probably published in either in applied mathematics journal or mostly they go to engineering journal. तर मैले देखेको चाहिँ हाम्रो एरियामा हामीले रिसर्च डिजाइन र रिसर्च मेथोडोलोजी भनेर त्यस्तो पिएचडीमा इभन मास्टरमा त्यस्तो कुनै त्यस्तो स्टडी गर्ने अथवा थिसिसमा पनि लेख्न पर्ने चाहिँ हुँदैन तर जो साथीहरू ऑप्टिमाइजेसनमा हुनुहुन्थ्यो जो साथीहरू चाहिँ स्ट्याटिस्टिक्समा हुनुहुन्थ्यो दे ह्याड टु डु द्याट बिकज देयर रिसर्च इज बेस्ड अन डिजाइनिङ रिसर्च एन्ड अल्सो एक्सपेरिमेन्ट्स. अर्को क्वेसन सुशीलजी को हात देख्छु मैले सुशीलजी सुशील has his hands up. Do you have any question?
नमस्कार सर
नमस्कार हजुर
सरले भन्न खोज्नुभएको थियो गुगलमा सर्च कसरी गर्ने भनेर नि सर त्यो
हजुर
त्यसलाई कन्टिन्यू गर्दा हुन्छ कि सर
ए ल होइन त्यसमा त अब जान्छु म यहाँ अलिकति मेरो अरू स्लाइड पनि छ तर मैले जो गुगलमा जान्छु होइन पहिला यहाँ चाहिँ मैले अनि यसमा चाहिँ अब फर इक्जाम्पल एउटा एउटा इक्जाम्पल लिउँ लाइक आई वान्ट टु सल्भ बाइहार्मोनिक इक्वेसन युजिङ अडाप्टिभ फाइनाइट एलिमेन्ट मेथड अडाप्टिभ फाइनाइट एलिमेन्ट तपाईँहरूलाई भनेको नि तपाईँहरूको एरियाको पनि प्रपोज गर्नु होला बाइहार्मोनिक इक्वेसन अडाप्टिभ फाइनाइट एलिमेन्ट मेथड अब तपाईँले Theory of Adaptive Finite Element Methods and Introduction यो किताब बुक आयो यो हैन बुक आयो इट इज साइटेड बाई 357 people and it is published in 2009 and अर्को 1974 मा आयो a mixed finite element method for the biharmonic equation Ciarle and Rabia. This is the classical paper where they propose a mixed finite element method for the biharmonic equation. Then there is another one is Morley finite element method for the eigenvalues of the biharmonic operator. There are so many papers. Now here Google Scholar always sort these items using citation index, citation 357, citation 373, and so on. Now I want to have adaptive in my sorts. Then I just enclose the adaptive by inverted commas, you see, and then now I get still I get the same book, Theory of Adaptive Finite Element Method, but then Morley comes before. And now the other thing also that now you can also look at how many people have cited this article. If you just click here, cited by 56, this article is cited by 56. I click here and I get the list of the papers which cited that paper. The Morley finite element paper, this Morley finite element method for the eigenvalues of the biharmonic operator. And now I can also use, for example, okay, I like this paper. I can also download this paper, PDF, Oxford University Press, OUP. I can download this. It's by Gallistel. It's a quite recent paper here. Now, can I download it or not? I can try here. It seems that I don't have access to this paper. I don't have any access to this paper. Then I normally go to my library to download this. Morley, I can go to library and download this paper. Or I can also get the citation data from here. Go to site. And then if you use Microsoft Word, you can use this kind of MLA, APA style citation, Chicago style, Harvard style, Vancouver style citation. But normally I use BibTeX. I go to BibTeX and copy this one. And then go to my text file, and then I just have this collection of all my papers in this bib file, total.bib. This is the file that I have all the collection. And here I use this one here, this article. Normally I use the standard Gallistel 15. I use the standard method of naming the article, 3 letters, family name of the author, and then the year of the publication, 15. Now this article is in my bibliography file. Let me quickly talk about the bibliography here, and we can talk about that. Like here, the bibliography here. You can use like, let me show you. Yeah, here, this paper, GAL 15, I can use Morley finite element method for eigenvalues of biharmonic equation is discussed in. Now cite the name of the article, GAL 15 here. I close this, and then I can now compile by using LaTeX, but it doesn't compile here. You can see the question mark here. What you need here is the go to LaTeX, go BibTeX, typeset, and then go to LaTeX again, compile once, still not coming, compile twice. Yeah, now you can see the number 1 is this, Gallistel paper here. Morley finite element method for the eigenvalues of the biharmonic operator. Now, how do you do this? By using you can use the normal LaTeX, or this is Beamer file. We use something like that here. Let me show you, what is that? Here. You can use this bibliography style at the end of the file, bibliography style. I use plain style. There are many other styles available like alpha, SIAM, UNSRT, ABRV. And then bibliography file is total.bib. This name of the file that I have opened here, total.bib is the name of this file. You can give any name. That was my name, total.bib, because I collect all the literature into this file, the B file where we store all literature relevant to our research. And where you put that, just before the in document, we include here. And what happens is that if we look at the last page, here we get all the references here. We get all the references here that we have cited in our research here. This can be quite useful in doing research and also including the relevant research in our research article. And the other thing that also I want to highlight is, for example, there's a paper, Hierarchical Conforming Finite Element Method for the Biharmonic Equation. Suppose I am interested in some mixed finite element using, let's say, using bi-orthogonal system. Let's say bi-orthogonal. You can make your source item really, really specific by including more words on the source. Like here, C0 linear finite element method for biharmonic problem. Okay, I want to see what they have done in that paper. The HTML file of that paper is available in Springer. Oh, service not available. Oh, that's not good. Let us try from here. I might have actually this article in my folder. The Springer link. I don't know. It's probably down now or something going wrong. Guo Zhang Zhou. Let me see if I have that paper with me. I make a folder here, all the electronic collection here. Open Guo Zhang. What was the Guo Zhang Zhou? Probably that paper I don't have. But whatever it is, the idea here is that when you download the paper, we want to look at first we look at the abstract very, very carefully. In this article, we propose and analyze an effective Hessian recovery strategy for the Lagrangian finite element method of arbitrary order. Now, if you are interested in Hessian recovery, then this is a really interesting article. We prove that the proposed Hessian recovery method preserved polynomial of degree k plus 1 on general unstructured meshes and superconverges at a rate of order of h power k on mildly structured meshes. That means this paper has some theoretical contribution as well. In addition, the method is proved to be ultra convergent, 2 order higher. That means if you are using polynomial of degree 1 finite element, you get the convergence of 3rd order here. It's called ultra convergence. For translation invariant finite element space of any order, numerical examples are presented to support our theoretical results. We can look at the introduction if we want to know what they have done, but we can go directly to the main part of the paper. Now you can see that what they have done is they have studied that problem by using different types of meshes here. In the finite element, you have always mesh here. Yeah. And that means it is not really general as I was thinking. And we can go down, then they have this is called the gradient recovery. From the gradient, they go to Hessian recovery. This is the Hessian, recovered Hessian actually. And then they have PPR, SPR, PPR, PPR. Now we have to understand what is this PPR, what is SPR. I know what is PPR is. PPR is polynomial preserving recovery. SPR is, I think, I don't know. SPR is also something polynomial recovery, but I don't remember exactly. Now, if I want to know that, then I have to search again in the Google Scholar and find what is that. And you can see all these formula they have developed for the Hessian, like a finite difference formulas. And we have these grids here. And if we can't really prove results for general type of grid, then they create certain grid. That means this method works for these kind of grids. And we can go down to look at the superconvergence analysis here. And then numerical tests are here. If we are interested in the numerical test, the convergence behavior are given here. Now again, I am back to question and answer. If you have any questions, let's discuss these questions. and I will move ahead.
हामीले बेसिकल्ली कुनै पनि कम्प्युटेसनल मेथड्सहरूलाई त्यसको भ्यालिडिटी दिनको लागि एनालाइटिकल र न्युमेरिकल मेथड चाहिँ आवश्यकतै हुन्छ होइन सर? र कहिले कहिले जस्तै हामीलाई थाहा छ पर्टिकुलर कुनै पनि प्रब्लमको एनालाइटिकल यसको सोल्युसन हुँदैन भनेर भन्नको लागि कुनै एउटा काउन्टर इक्जाम्पल दिन पर्छ कि त्यसको नन लिनियरिटी भेरिएबल कोफिसिएन्ट र हायर डिग्रीहरू चेक गर्नुपर्छ, अथवा डाइरेक्ट भनिदिए पनि हुन्छ कि इट डज नट ह्याभ दिस एनालाइटिकल सोल्युसन, सो वी गो थ्रु दि न्युमेरिकल सोल्युसन गर्न सकिन्छ, अथवा यसको केही सर्टकट केही प्रोसेस छ होला, इट डज नट ह्याभ दिस एनालाइटिकल सोल्युसन, सो वी मुभ फरवर्ड टु दि न्युमेरिकल भनेर अनि बल्ल त्यही प्रोसिजर अनुसार कुनै पर्टिकुलर प्रब्लमलाई गर्न सकिन्छ कि के होला सर भनेर जिज्ञासा।
एकदमै very interesting and very profound question this is. It is not easy always to say that this problem doesn't have an analytic solution. You may not have, but somebody else might, create analytic solution for that one. Most of the time, what we do is you can go to, try yourself first, and then you can go to some symbolic software and try Maple, Mathematica, etc. But most of the nonlinear problems, they don't have analytic solution. You can, if it is really nonlinear, then you can say that this is nonlinear problem, we don't have analytic solution. And also, most of the analytic solution depend on very simplified boundary conditions. If we are talking about partial differential equation, and the analytic solution cannot be found if you have more complicated boundary conditions, for example. In that kind of thing, sometimes we might make mistake, like we say that there is no analytic solution, or better say that we can't really find analytic solution. Rather than we say there is no analytic solution, we can say that we could not find any analytic solution. That would be more honest expression. If I say there is no analytic solution, then that means the solution may not exist, but most of the time there is no analytic solution in the closed form. Like expressing using exponential, cosine, sine, logarithm, etc. But what I will write is that we don't have, we can say that we don't have analytic solution for this nonlinear problem in a closed form. If we say something like that, that will sound that we don't know. But if you say that it doesn't have any analytic solution, then that means if you don't have any analytic solution, then somebody else might be able to find. That way it will not be really 100% correct to write like that. It always comes from thinking. When you write something, then you think whether this is actually correct or not. And other thing that experience with my PhD students, they wrote sometimes, this problem doesn't have a solution. I mean, if you say this problem doesn't have any solution, that means there is no reason to apply a numerical technique. If the problem doesn't have a solution, then what is the point of applying a numerical technique? The important thing is that this problem has a solution, but the analytic solution cannot be expressed in a closed form, or analytic solution cannot be derived. Like if you look at Lamichhane, for example, one of the biggest theory, biggest theoretical help in our area is the Lamichhane lemma. Lamichhane lemma tells that if these conditions are satisfied, certain variational problem has a unique solution. But this theorem does not tell us how to derive the solution. It does tell that there is a solution. And in that kind of theory, it's always useful to apply numerical technique. Now the validation. How do we validate? Assume that we don't have numeric analytic solution for a certain problem in a closed form. How do we validate our numerical approximation? This is a question that everyone in our area asks. In mathematics, if you don't have analytic solution, you get solution by using some computer algorithm. Now you ask yourself, is the solution that I derive by using computer is realistic? Is it actually the solution of the given problem? You can do the following. You can do compute the numerical solution by using really refined grid. If you are starting from 10 by 10 in 2 dimensions, for example, 10 by 10, you can go to 1,000 by 1,000, maybe 100,000 by 100,000 grid. Compute the solution in a very fine grid. Now you go back and compute the solution in 10 by 10, 20 by 20, 40 by 40, and in such a range. And then now you can compute the difference between your coarse grid solution and your fine grid solution. You need some practice there. You have to do some interpolation to do the error calculation, but you can always do that. Compute a fine grid solution, which is often called a reference solution, and compute coarse grid solution, and from coarse grid to fine grid, compute the error. Like you can compute L2 error, you can also compute H1 error, which is okay in finite element. And if the error is behaving like what you get from theory, then you can say that your algorithm is producing reasonable results. But sometimes it is really difficult task, because you have to, if you are in 3 dimension, you have to compute solution in a very fine grid, can be time consuming. And also computing the error can be also pretty time consuming unless you get some already developed finite element or some code. But when you do that, more and more, then you will get that, you learn that from the experience. Yeah.
Thank you. Thank you so much, sir.
You're welcome. Any further questions? If not, let me go back to discuss a little bit about the papers. Okay. Before that, I really want to show, or I want to discuss my research in one area, how I extended my research, and how you can also do the similar extension in your area as well. This is just an example from my perspective. Okay. Initially, when I joined as a PhD student, my master thesis was in meshless method. It was not connected with my PhD research. I was given a task in the area of the non-conforming discretization of partial differential equation using bi-orthogonal systems. That was the initial task. In that area, my professor has already developed a bi-orthogonal system for the linear finite element method. And that is the case. The linear means that k is equal to 1. Normally, when you have linear finite element or linear polynomial, it's just linear polynomial, like in one dimension, it will be ax plus b. In 2 dimension would be ax plus by plus c. This is the linear. Go to quadratic. We are talking about 2 dimension. Then quadratic ax square plus bxy plus cy square plus dx plus uy plus f. This is quadratic. This is k is equal to 2. You can go to, now you can go to cubic, you can go to quartic, and then quintic, and 6th order, and so on. Then my task, the first task was this. I have to extend this to quadratic. That was my first task, which was quite easy. My first paper was to extend this approach to the quadratic finite element method. This is for k is equal to 2. And that was the paper which was published within a year or so. And then this was my first paper. Then I had to apply the bi-orthogonal system to interface problem. We discussed that problem also in our group, and then I applied to interface problem. The interface problem is a problem where you have, you have like 2 different domains, say D1 and D2. Then there is an interface here. On the interface, you may have the solution. The solution may have jump. That means solution at D1 minus solution D2 would be not 0. And also you can have the normal derivative, nabla U1 minus nabla U2. The normal derivative may have also jump here. This is the Dirichlet jump. This is a Neumann jump. And that was my second paper. You can see the connection. First bi-orthogonal to the quadratic, then bi-orthogonal to the interface problem. The third paper was to extend this idea to 3-dimensional problems. And then I go to 3-dimensional. Here I also developed most of the theory, underlying theory for the non-conforming method. Then another paper was to extend this idea to any k. It should be fine for any k, means the cubic, quartic, or any k. K can be 20, 30, and so on. That was another paper. And this paper was published in Mathematics of Computation. Then in my PhD time, I also worked on mixed finite element methods. That was a problem coming from the elasticity. Now you can see how I extended my research. I combined the bi-orthogonal system with the mixed finite element method. You can see here, bi-orthogonal system and mixed finite element. And now I can combine these two ideas together. And then we get another paper where I applied the bi-orthogonal system to mixed finite element methods. Actually, I applied to the simple mixed finite element. Later on, we applied to more complicated Hubasitsu formulation here. We also applied to Hubasitsu formulation. That was done when I joined here in Newcastle with some engineers in South Africa, and I think one of them is probably in the UK. And then I applied bi-orthogonal system to biharmonic problems, elasticity, and thin plate spline problems. Then you can see that when we do research, that means research means combining ideas. Okay, that's one thing I really want to highlight here. Research means combining ideas. Okay, there is nothing actually new here. Combining ideas. We say new ideas, novel ideas, of course, novel ideas, but this is combining the existing ideas. Like we have this conservation of energy principle. Nothing can be created, nothing can be destroyed. This has already been expressed in Gita. There is a certain verse of Gita where Krishna told that nothing can be destroyed and nothing can be created. Whatever is there from the very beginning, and they will last until the end. And this also is valid for the ideas as well. And there is nothing actually new. If you look at very carefully, all the research is done by combining the existing ideas. Now, if you have here, if you have like idea 1, for example, idea 1, you have another idea 2, like one idea is bi-orthogonal, another idea is mixed finite element. Maybe, you have also idea 0, for example, biharmonic equation. These 3 ideas we combine. And then we get new idea here. And what happens is that the bigger the jump from the existing idea, the more is your contribution. And the more is your contribution, the better journal you can aim for your article. You can publish in a better journal. And there is also sometimes you guys know that people talk here a lot about the epsilon paper. Epsilon, maybe should write here, epsilon paper. This is widely discussed in numerical analysis area. What is epsilon paper? Epsilon paper means that you have already one paper, you make epsilon difference in that paper, and then you get new paper. And this is regarded as a bad practice. This is a bad practice. It's not really good practice. But I think even the epsilon idea would be good in my opinion. I think you can publish in some reasonable journal if the idea is really, really good and appealing. And the one thing is that you find some interesting idea, you have some interesting problem, you solve that problem, you send that problem to a journal, and then referee looks at that problem and then see, oh, what is this? That means the problem that you have worked on, the idea that you have developed should be interesting to other people as well. If it is only interesting to you, then it cannot be published. And sometimes it can be a conflict of interest or something like that. It might go to a bad referee, and they might not find your idea interesting, but then you can submit to another journal. But it's really important that you talk to your supervisor, you talk to your friends, you talk to your colleagues about your ideas, so that you can consolidate. You can consolidate your ideas, and also you can convince yourself that your idea is really good. And then your colleagues can comment whether your idea is good or bad. And my strategy in research is to read as many papers as I can. Like if I'm working on biharmonic equation, mixed finite element method, then I read a lot of papers. And now my area is bi-orthogonal system. And if I work on bi-orthogonal system, there are not really many people working in that area. And if I write a paper on bi-orthogonal system, it is reasonably, there is low risk of someone already publishing what I am actually working on. That can happen. Sometimes you are working on something, and in that time you are working, somebody might publish on the same topic, and then your work may not be published. But for PhD, this is okay, because your supervisor still can say that your work is original. But for after PhD, like in my situation, that will be, that idea cannot be published. It is not necessary that we understand the whole content of the paper. Sufficient if we get the main idea of the paper. The details can be studied later when necessary. And the important thing is that we have to ask questions ourselves. What can be a new problem to research and source problem thoroughly, like in Google Scholar. And publication of research is, of course, very important. I think everybody knows that. And we have already done this, that we have tried to sort something on Google Scholar. Like you can, okay, the one thing that homotopy, probably you guys know what homotopy method is. Like if you want to look at homotopy method and numerical approximation, and then you can do Google search and find something interesting there. The one thing what I also found is that you may have some nice ideas, but if that idea is not written pretty well, not expressed well, it's pretty difficult to sell. It's like publishing is like selling your product in the market. And selling a product is it depends on other person, whether they like your product or not. That is why when we write, we have to make our writing precise, concise, and really appealing. And it's really important that you talk about your writing with your colleagues and also with your supervisor if you have one. Okay, extensive research of literature to write an introduction. And the introduction in my area, you can write in many different ways, but what I do is the following in the introduction. The abstract is a summary of your work, but in the introduction, the first part of the paragraph is generic and short. Like if I'm working on a biharmonic problem is really an important problem in our in science and engineering. This problem is used in the following strokes, fluid flow, thin plate splines, and so on. That will be the first part of the introduction. In the second part, we expand the first part, giving more details and some specific areas, including literature review. Like if we are planning to use some mixed finite element methods, then we have to outline if people have already used mixed finite element methods. Okay, these people have already developed mixed finite element methods for biharmonic problem in the following papers, and they have also developed like adaptive finite elements. Whatever they have done, that has to be described in the second part. In the third part, introduce what will be done in this paper. In this paper, we are going to introduce application of bi-orthogonal system or something like that, or we are going to derive optimal a priori error estimate for the following formulation of the biharmonic problem, so on. This part will be mainly for the paper. The fourth part, normally the structure of the paper has the following structure, or the paper is organized as follow. In section 1, I'll do the following. In section 2, I do the following, and so on. This is the fourth part. And then we discuss the main part of the paper. We have the presentation of the problem. You present the biharmonic problem in the variational formulation where finite element application is possible, present solution approaches, and theory for the problem. For example, existence, uniqueness, and stability theory, how the solution behaves, and so on. What is for example, in some area, asymptotic behavior of the solution, and the numerical approaches. We apply some numerics, and then discuss the numerical approaches, how we apply, and so on. Then stability of the numerical approach, the complexity, how difficult it is, how time consuming it is, existence, uniqueness, and stability of our discrete problem, for example. And then we present some numerical simulation examples to validate that our approach is actually good. And then finally, conclusion. In some journal, you don't need to write conclusion. Also acknowledgement if you have used some funding from somewhere. This part we have already done, the bibliography part. And I just want to briefly discuss the what is a good paper. I get paper to review almost probably one paper a month or so. Of course, I can't do this. I decline most of the time. I can't really review one paper a month. Maybe one paper in 2-3 months I review. And what kind of paper I find really good? Of course, the results should be pretty good, but mathematical correctness and no typos. If there are a lot of typos, then it shows that the paper was not written carefully. The authors are not really careful and precise and concise. abstract, introduction, sections, and conclusion are clear. The conclusion is actually not necessary, but all the distinction clear. And there is also, there should be some novelty. The contribution of the paper are well expressed and the background of the research is clearly outlined. Recently, I referred a paper. The paper was really well written, nice, very nice, written by some US professors. I looked at the paper. I think the results were quite good. All no typos. Mathematical correctness was there, precise and concise. Slightly, I think it was longer than expected. Otherwise, everything was fine. But later on, I found that the theory they have used was already published for the biharmonic problem, and they extended that to the sixth order problem. They go from biharmonic to the sixth order, and it was very similar. And there was not really novel contribution also in the numerical analysis. Then I thought whether I should reject that paper or give them chance to do the major revision. But then if I give them chance to do the major revision, then what will they do? How can they improve the paper? Then I don't see any possibility of improvement. And then finally I had to reject that paper. But the paper was actually should be publishable in lower ranked journal, but the journal they were sending was a bit higher ranked journal, and that is how I rejected that paper. Of course, I gave all the details why I am rejecting the paper. And sometimes that means that the ideas, the strength of the ideas also really, really important. And now I think I stop here for a moment and then open for the discussion again. Any questions?
तो होमोटोपी भनेको हाम्रो टोपोलोजी पर्सपेक्टिभ हो कि होमोटोपी पर्ट्रिब्युसन मेथड हो सर? त्यो मेथड युज गर्नुभएको थिएन हजुर सर?
ल होमोटोपी भनेको चाहिँ अब इट्स काइन्ड अफ फङ्सन. होमोटोपी भनेको अब एउटा पर्टर्बेसन मेथडमा पनि होमोटोपी युज हुन्छ. Homotopy, you can also use solving the ordinary differential equation. You can use them to solve also nonlinear equation. Homotopy is like a function from 0, 1 to something. I can probably show you. Homotopy, this is the definition. Homotopy between two continuous functions f and g from the topological space x to a topological space y, defined to be a continuous function h, x cross 0, 1 to y from the product of the space x with the unit interval to y, such that this is these homotopy conditions are satisfied. This is the standard definition of the homotopy.
Algebraic topology ko kura ho yo.
This homotopy can be used in many areas. Like we have applied also in nonlinear equation. I have applied in solving ordinary differential equation, and also in perturbation theory they use homotopy a lot. But this is the, I think, definition from the algebraic topology definition. But in numerical analysis, this is similar definition, but I think they are probably not X here. This is really useful. By the way, the homotopy approach is extremely useful in many areas. You can also apply in solving, probably it can be useful for Shankar as well if you want to apply in your fractional.
Yes, yes. Sir.
Yeah, might be. We don't know. One has to exploit every direction. Let me see homotopy. And there are very, very easy books as well where they describe application of homotopy for like differential equation, perturbation method, and so on. I'm using this numerical analysis book by Borden and Fierce. Probably you guys know this book. And this one they use, they have the same type of homotopy, which is the same as x cross 0, 1, where x in this setting is a Euclidean space, not really any sort of difficult topological space. This x is just the Euclidean space, vector space, and y is another vector space, and that makes our life much easier. Like you can see that here also the homotopy between two embeddings, and by using that you can solve some nonlinear problems. I have actually applied homotopy to differential equation, but I have not got time to write it properly. I think it can be published. It was a summer project I gave to one student, and they applied homotopy to compute, I think, the solution of the boundary value problem. Okay, I think that is all so far. I can briefly talk about something about research writing, but if you don't have any question, I go to briefly discuss about writing a proposal. This is something like that. If you want to go to a PhD, especially in Australia, a proposal is necessary, kind of research proposal. Although that proposal will be modified, that proposal will be updated when they start the PhD. But proposal writing is important. And how we write proposal is that the first you have to identify the problem. Maybe I go back to, for the proposal writing, I'll mainly only discuss the main components and then probably finish today. The first step in writing a proposal is to identify a problem to study. You have to first identify, okay, I want to study homotopy method and numerical approximation. Actually, I wanted to look at that also from the, let's look at that from the Google Scholar, what it says. One example can be, go here, and then I have Google Scholar, homotopy, numerical approximation, for example. And then it will, and you can also see that, you want to see only the papers in the recent area by clicking here, apply on the optimal selection of the linear operator and the initial approximation in the application of the homotopy analysis method to nonlinear fractional or differential equation. Look, Shankar, somebody has done, you see, we have just thought about this and somebody has already published some application on the optimal selection of the linear operator and the initial approximation in the application of the homotopy analysis method to nonlinear fractional differential equation. Yeah, you can get a lot of information through Google Scholar. Now, briefly, let me discuss the proposal writing, and then we can finish. Okay, the first step in proposal writing is to identify a problem. Most of the time, one has to discuss with possible supervisors to write the proposal. And then second step is conduct extensive literature search and find how other people have tackled the problem and pinpoint your ideas to solve the problem. What is the main contribution? What will be the main contribution in the research that has to be explained? And one needs some imagination and cognitive skills to connect the already existing theory and approaches to solve a new problem. Some sort of connection we need to discuss here. And for the research proposal, we need a title and abstract of the proposal. And then we need a statement of the problem and topic. We need to identify the subject area and explain reasons why the study is important. It's always marketing. We have to identify the area and also explain why that is really an important research problem. And then literature review, contextualize your research proposal. That means, okay, A, B, and C, they have done this kind of problem, this kind of work in this problem. D has done the following problem. E has done this, and now I will do this. Based on those works done by these people, I am probably developing some new algorithms for this problem, or I am doing, proving some theorems or something like that. Also discuss how the existing research studies are linked to your research proposal. It's pretty like a paper, but here in the proposal, we are not solving, we are just proposing something here. Method, approach, and time scale. We have already discussed that. Here we describe how you carried out the research study to reach the research outcomes you have described in the research topic section. You may include particular theorems or theory to be used in your research study. You also show how you can realistically complete the research within the time frame. This is also important that, okay, I can finish that in 2 years or something like that. And then lastly, we list all relevant references here. And then master level and PhD level research proposal can be different. A research problem can be different. In the master level, the novelty can be quite minimal. Survey article can be a master. If you do survey in this homotopy approximation, it can be a good master thesis. Even if you work on something like how to apply homotopy method for fractional differential equation, that would be a nice topic for a master level. For a PhD, something really innovative needs to be done. For example, in Australia, master thesis is for 2 years if it is master by research. But in Australia, we have also honors program. Honors program is 6 months research, which can be quite a small research project. In many countries, a master thesis is a small component in the whole degree. Yes, I'll send the slides here. That's fine. And for the there are some examples for the master level project. For the PhD level, should be much more deeper than the master thesis project. It should have vertical and horizontal depth. Vertical means that it should go deeper, and horizontal means that it should also understand similar approaches in other areas. In most countries, a PhD work spans around 3 to 4 years. In Australia, it is expected that a student finishes their PhD in 3.5 years. They can go over 4 years. Students are discouraged here to go over time, must. And here there are some examples for the PhD level topic. And there are also some examples that I have listed here for my current and past PhD students. I think probably I should stop and ask if you have any questions or comment. I'll send the slides. What was the email address? So if you have any questions, I'm happy to stay here a few, maybe 10-20 minutes. If not, then we can finish.
सरलाई धेरै एकदम धेरै धन्यवाद। यहाँ जीवन सर भर्खर कता एकछिन व्यस्त हुन्छु भन्ने कुरा थियो। म हरि गिमाली बोल्दैछु सर।
हरिजी हजुर।
यो टाइममा यस्तो टाइममा मजाले यति लामो सेसन चाहिँ एकदम मजासँग खटेर पुरा हामीलाई चाहिएका कुराहरू मजासँग चाहिँ सरले इन्फर्मेसन दिनुभयो। हामी सबैलाई यो अहिले चाहिए पनि थियो। फेरि पनि आवश्यक पर्यो भने हामीलाई रिक्वेस्ट गर्न सक्छौँ सर। आजको लागि चाहिँ धेरै धन्यवाद लागि र यो सेसनलाई सरलाई धन्यवाद दिनु हुन र यो सेसनलाई चाहिँ अन्त्य गर्न हाम्रा अध्यक्षज्यू पारी सरलाई चाहिँ म हार्दिक अनुरोध गर्छु।
एक धन्यवाद सर। मैले सबै सरहरूलाई वास्तवमा आजको यो कार्यक्रम चाहिँ एकदमै राम्रोसँग मैले एकदम इन्जोय गरेँ र के भयो मलाई लाग्छ हाम्रा साथीहरू सबैले एकदम राम्रोसँग इन्जोय गर्नु हो। किनभने के भयो रिसर्च इन म्याथमेटिक्स भनेको हैन के भन्छ सबैलाई चाहिने यो चाहिँ हाम्रो ब्याचलर मास्टर एमफिल पिएचडी र पिएचडी गरिसकेका इभन प्रोफेसरसम्म चाहिने कुरा हो। र उहाँले चाहिँ अहिले सबैलाई समेटेर सबैले बुझ्ने भाषामा एकदम राम्रोसँग चाहिँ नि सरले हामीलाई सिकाउनु हो र चाहिँ सरले आफ्नो सेयर पनि गर्नुभयो र सरले के भन्दा एकदमै धेरै मोटिभेटिभ इन्ट्रेस्टिङ र पर्सुएसिभ तरिकाले सिकाउनु हो र चाहिँ नि खास गरिकन यो रिसर्चका कुरा सरले चाहिँ नि अहिले यो आजकोमा यो चाहिँ प्योर म्याथमेटिक्स एप्लाइड म्याथमेटिक्स अथवा के भन्छ कम्प्युटेसनल म्याथमेटिक्स जस्तोसुकै म्याथमेटिक्सलाई पनि सरले एकदमै फाइदा हुने तरिकाले गर्नुभयो। चाहे जस्तोसुकै म्याथमेटिक्स गरे पनि अब हामी कन्टेन्टमा चाहिँ हामी एकदम स्ट्रङ बन्नुपर्छ। हाम्रो कन्टेन्ट सिस्टेमेटिक एकदम स्ट्रङ भयो भने हामी जहाँ पनि पुग्न सकिन्छ हो। त्यस कारणले गर्दाखेरि यो हाम्रो नलेज गेनका कुरा हो र चाहिँ यसमा खास गरिकन चाहिँ नि म्याथमेटिक्सको आइडियालाई हामीले कसरी रिसर्चमा लाने भन्दाखेरि यो एनालाइटिक सोल्युसन अथवा चाहिँ न्युमेरिकल सोल्युसन अथवा हाम्रो कम्प्युटरबाट सिमुलेसन गर्ने अथवा यो हाम्रो म्याथमेटिकल मोडेलिङ चाहे जसरी गरे पनि हामीले हाम्रो रिसर्च आइडियालाई हामीले एक्सपान्ड गर्न सकिन्छ र चाहिँ नि त्यसमा आफूले प्रोपर नलेज हुनुपर्छ जस्तो लाग्छ। र चाहिँ अबको रिसर्च भनेको चाहिँ नि हामीले के एकाडेमिक जब अथवा हामीले न्यू करियर अथवा चाहिँ नि फर्दर स्टडी अथवा जे गरे पनि यो एकदमै हामीलाई जरुरी छ जस्तो लाग्छ। र सरले चाहिँ धेरै कुरा यसमा चाहिँ भन्नुभयो। यो चाहिँ नि हाम्रो चाहिँ नि जसले रिसर्च गर्नुपर्छ ऊ के भन्दाखेरि कन्फ्युज हुनु भएन र रिसर्चको चाहिँ उसको के भन्छ मेथड प्रष्ट हुनु पर्यो, क्लियर हुनु पर्यो, अब्जेक्टिभ प्रष्ट हुनु पर्यो र चाहिँ नि हाम्रो इथिक्स मेन कुरो इथिक्स रहेछ कि इथिक्समा पनि हामीले चाहिँ नि गर्नु पर्यो र हाम्रो कहिलेकाहीँ रिसर्च गर्दाखेरि कहिलेकाहीँ हाम्रो गलत हाम्रो नोभेल्टी चाहिँ नि भइदिएन भने हाम्रो अर्थको अनर्थ राख्छ। हाम्रो त्यसैले हामी रिसर्च गर्दाखेरि हामीले भ्यालिडिटी खास भ्यालिडिटी चाहिँ नि एकदमै ध्यान दिनुपर्छ। धेरै सोचेर एकदम लट्स अफ थिङ्किङ गरेर हामीले एकदमै विचार गर्नुपर्छ। त्यसैले अनेस्ट सबभन्दा ठुलो कुरो भने अनेस्ट रहेछ। अनेस्टलाई र चाहिँ नि त्यस कारण हामीले प्रोपर साइटेसन गर्नुपर्छ र चाहिँ अरूको हामीले कपी चाहिँ गर्नै हुन्न। र चाहिँ नि एउटा सबभन्दा गल्ती के हो भने हामीले डोन्ट पब्लिस के भन्छ रङ थिङ पब्लिस गर्नुहुन्न भनेर सरले पनि धेरै कुरा भन्नुभयो हो। त्यस कारणले गर्दाखेरि हामीले रिसर्च गर्ने र नगर्नेको बिचमा पनि धेरै फरक हामीले पाइएको छ हो। त्यस कारणले गर्दा रिसर्च गर्दाखेरि हामीले कन्साइज प्रिसाइज र चाहिँ वेल एक्सेप्टेड र चाहिँ सबैले बुझ्ने तरिकाले र भ्यालिडेट त्यस्ता कुराहरूलाई चाहिँ एकदम विशेष ध्यान दिनुपर्छ। र चाहिँ सरले आज हामीले के भन्छ जर्नलका कुराहरू पनि एकदमै गर्नुभयो। हामीले के भन्छ प्रेजेन्टेसन कसरी गर्ने कुरा गर्नुभयो र हाम्रो लिटरेचर रिभ्यू लिटरेचर चाहिँ हामीले कसरी खोज्ने कुरा गर्नुभयो। यी सबै कुराहरू अब हाम्रो बायोग्राफीका कुराहरू साइटेसनका कुराहरू अनि चाहिँ नि हामीले पेपरमा का चाहिँ डिफ्रेन्ट पार्टलाई हामीले कसरी एडजस्ट गर्ने, कसरी मिलाउने कुराहरू, यी सबै कुराहरू चाहिँ नि गर्नुभयो। एकदम अब हाम्रो नेपाल गणित समाजले चाहिँ सरलाई यत्रो धेरै समय सरको त्यहाँको अनुकूल, त्यहाँको टाइम अनुकूल प्रतिकूल छ जस्तो लाग्छ अझै पनि, किनभने त त्यो हाम्रो टाइमको ग्यापले हो, तै पनि सरले चाहिँ नि धेरै कुराले हामीलाई सचेत पनि बनाउनु भयो, धेरै कुरा सिकाउनु भयो पनि, र सबै कुरा सिकाउनु भयो, र चाहिँ नि के भन्छ नेपाल गणित समाज होइन अब सरलाई एकदम धेरै धेरै धन्यवाद दिन चाहन्छ। र फेरि पनि आउने दिनमा पनि हामी के भन्छ नेपाल गणित समाजलाई होइन सरको चाहिँ सपोर्ट, समर्थन, साथ र चाहिँ एकदम रहिरहेछ, र सरको चाहिँ नलेज, स्किल र एक्सपर्टाइजलाई एकदम नेपाल गणित समाज भरपुर चाहिँ नि प्रयोग गर्न चाहन्छ होइन। अब मैले यति भन्दै र हाम्रो आजको कार्यक्रममा उपस्थित सम्पूर्ण साथीहरूलाई मैले हार्दिक धन्यवाद व्यक्त गर्दै आजको कार्यक्रम यही सकिन्छ। एकदम थ्याङ्क यू भेरी मच है त सबै साथीहरूलाई।
Thank you everyone. It was my
Namaskar.
pleasure to talk about that. Thank you. Yeah. Thank you. Yeah.